Topic 7.1 Summary, Part 3, Radioactive Decay. Most nuclides are unstable. This was first researched by Henri Becquerel, Pierre Curie, and Marie Curie. Particles are given off when the nucleus of an unstable atom randomly and spontaneously decays. This causes the emission of ionizing radiation. Spontaneous emission of ionizing radiation is called radioactivity. Here are a couple of terms that you need to know. When a nucleus decays and turns into something else, the nucleus before the decay is called the parent nucleus. The resulting nucleus after the decay is called the daughter nucleus. There are several ways to detect ionizing radiation. Henri Becquerel first used photographic film to show the existence of X-rays. A Geiger-Müller tube is part of a device called a Geiger counter, which can be used to measure ionizing radiation. And there are some elements that when they are struck by ionizing radiation will give off visible light. Those materials are called fluorescent elements, so that's another way to detect ionizing radiation. And today there are many types of detectors that can be used for measuring ionizing radiation. A magnetic field can be used to differentiate among alpha, beta, and gamma radiation. Using the right-hand rule, you should be able to confirm that when a positive particle moves in this picture from the source at the left through the magnetic field, which is into the screen, a positive particle is going to move to the left. So that's why you see the alpha on the upward arrow. A negative particle, such as a negative beta, an electron, would move to curve to the right. Again, you can determine that by using your right-hand rule. And since a gamma ray has no charge at all, it's not affected at all by a magnetic field, and that's why you see in the picture that the gamma ray will go straight through the magnetic field. Ionizing radiation can be classified into three types. Alpha particles are positive, and an alpha particle is a helium nucleus, so it has a mass number of 4 and a charge of +2. Beta particles are high-speed electrons or positrons. We'll talk a little more about positrons later, but a positron is just like an electron, has the same mass, but it's positive. And gamma rays are high-energy photons. They're electromagnetic waves with very, very short wavelengths, high frequencies, and therefore lots of energy. So why is it called ionizing radiation, and why should we care? Well, you might remember from chemistry that to ionize an atom means to remove one or more electrons from that atom. And you also should recall from chemistry that it's the electron configuration that determines how atoms will bond. So removing electrons from an atom will change the ability of the atoms to bond, breaking the bonds, forming molecules. If ionizing radiation breaks DNA or RNA bonds, it can damage cells, potentially causing a cancer. It's important to understand that not all radiation is ionizing radiation. So for example, infrared light, radio waves, visible light, they're all forms of radiation. They're electromagnetic radiation, but they are not ionizing. They can't break bonds. They can't cause cancer. Only ionizing radiation can break bonds. Here's a handy chart which summarizes some of the characteristics of alpha, beta, and gamma radiation. So if we take a look here, let's talk about the alpha particle first. Okay, so an alpha particle is a helium nucleus, as we've said before. So because it's a helium nucleus, it has a charge of +2, because there are 2 protons in a helium nucleus. And its mass is 6.64 times 10 to the negative 27 kilograms. Again, that's twice the mass of a proton. And an alpha particle will only penetrate a few centimeters of air. Alpha particles, you can think of, they're like big lumbering trucks. They're heavy, they have a lot of mass, 2 protons and 2 neutrons, and they have a lot of charge, and so they're likely to collide with atoms on their way. This next row here, ions per millimeter of air, is going to take a little more explanation, but basically as a A charged particle, an ionizing particle or an ionizing radiation passes through material, it interacts with matter. And so this is saying that when alpha particles travel through air, on average, they're going to have about 10,000 interactions, cause about 10,000 ionizations for every linear millimeter that they travel. That's a lot. And for detection, alpha particles affect photographic film, and they're affected by electric and magnetic fields. All right, let's talk about betas. A beta particle is a fast electron, or it can be a fast positron, okay? The charge on a beta particle, a negative beta, is negative 1, because it's an electron. But we're also going to find out that there are positive beta particles, and a positive beta particle consists of a positron, which is just like an electron, but it's positive. The mass of a beta particle is simply the mass of an electron, 9.11 times 10 to the negative 31 kilograms. And a beta particle will travel farther than alpha will. It'll go through a few millimeters of metal. It causes a lot less ionization than alpha, about 100 times less ionization than alpha does. And it can be detected because it affects photographic film, and it's affected by electric and magnetic fields. Okay, finally, let's talk about a gamma ray. So a gamma ray is a high energy photon. It's an electromagnetic wave, okay? It has no charge because electromagnetic waves have no charge. It has no mass, okay? And it has quite a bit of penetrating ability. It can go through many centimeters of lead, okay? But the good news is it does not cause a lot of ionization. In fact, you can see that the amount of ionization per millimeter of linear travel is only 1/10,000th that of an alpha particle. And gammas affect photographic film like the other two forms of radiation do, but gamma is not affected by electric and magnetic fields. That's because it does not have any charge. Again, here's a little summary of the amount of penetrating power of different forms of radiation. As you can see, alpha particles don't penetrate very well. In fact, an alpha particle will be stopped by a sheet of paper. Beta particles will go through paper, but they might be stopped by plastic. Gamma and X-rays will go through paper and plastic, but they'll be stopped by lead. And neutrons will pass through paper, plastic, and lead, but they can be stopped by many feet of concrete. The greater the number of protons in a nucleus, the greater the repulsive force trying to break the nucleus apart. That's, of course, because protons, all being positive, repel one another. Neutrons contribute to the strong nuclear force, which keeps the nucleus together. As a result, large nuclei need more neutrons if they are to be stable. A Segre plot, shown here in this diagram, is a graph with the number of protons on the y-axis and the number of neutrons on the x-axis. The black line in the graph is the stable nuclei. And notice that the black line curves slightly to the right, slightly below a 45-degree angle line would, and that indicates that large stable nuclei tend to have more neutrons. Okay, that's all, folks. Except I do have a wacky definition for you today. Today's word is burglarize. Burglarize. What a crook sees through.